Hello everyone, welcome to the next session on Advanced ANSYS Workbench tutorials. In this session, we will analyze a ball valve for its static structural analysis. We will start by double-clicking on Static Structural module. We'll first go to Engineering Data and double-click. Engineering Data Sources, General Materials. One of the material which we will be using for the analysis is stainless steel. Then we click on Engineering Data Sources again, and I'm going to add two more materials. One is brass, for which we will give the value of density as 8490 kg per meter cube. Then we'll click on brass again and double click on isotropic elasticity. We will give the value of Young's modulus in gigapascal. It is 97 and the value of Poisson's ratio is 0.31. Then we'll click on brass again and we will give the value of tensile yield strength in megapascal. This value is 310. Also, we will give the value of tensile ultimate strength in megapascal. It is 469. Then we will add another material which is CPVC. This is a plastic material which is also used commonly for making of the ball valves. We will first give the value of density. It is 1650 kg per meter cube. Then we'll click on CPVC again and double click on isotropic elasticity. We will give the value of Young's modulus in gigapascal. It is 3.4. Value of Poisson's ratio is 0.35. Again, we'll click on CPVC and double click on tensile yield strength in megapascal. The value is 52 and we will give tensile ultimate strength in megapascal. It is 58. Now that we have given all the properties, we will go to project and update project. Then we will right click on geometry and add the material and import the geometry which is already made with us. Then we'll go to model and double click. We'll first go to geometry and click on this plus sign here. We will select all the three parts and we'll first give the material as stainless steel. Then we'll go to mesh and generate the default size of the mesh itself. Then we'll go to static structural A5, right click here and insert fix support. Here we'll choose the face option. This is one of the face and this is the other side. We'll click on apply. Then we'll right click and insert pressure on the internal surfaces. Then we'll click on apply. This value I'm going to give as 2 megapascal. Then I'll right click here and insert moment. This connecting rod is going to be subjected to moment. I'll change vector to component. Along the Z direction, I will give the value as say 200 Newton meter. Then we go to solution, right click, insert deformation total. We'll insert deformation directional. I want to see the deformation along the y-axis. Right click, insert strain equivalent. Right click, insert stress equivalent. We will also right click and insert stress tool, max equivalent. Here you can get the value of safety factor. So we'll go to solution A6 and solve now. We'll first go to total deformation. You can see here the value is 0.108 mm. You can animate and check the pattern of its motion. Next, we'll go for directional deformation along the y-axis. Here you can see the maximum deformation is 0.10857 mm. Then we'll go for equivalent elastic strain. 0.00309 is the maximum value. Then we'll go for the value of stress. It is 525.74 megapascal. You can animate and check this result. But over this body maximum is blue color, which is over here. So you can just go to probe and you can just click over here. You can see the value is very less. Now where it is maximum is along this small shaft at the central end, because that is the point where you have given the moment. Then we'll go for safety factor. Again you can see that this is the point where your body is not safe, but apart from that the body is completely safe. So you have to be very careful when you give the value of moment. If it is this value which is very less, so you can just click on probe and check. Inside it is 0.8 and this portion yellow is 3.67. So yellow is okay, but this red portion is 0.78, which means the safety factor is very low. So to increase that, what you can do is you can change the value of this moment. If that value reduces, then obviously your safety factor will increase, which means for a particular value of pressure and moment, you have to be very careful such that your entire valve remains safe. So once this is done, we will now change the material. We will select all three of them. We will change it to brass. We go to solution A6 and solve once again. We'll go for the first result of total deformation. Maximum value is 0.216 mm for this entire valve. You can again animate and see the result. The pattern of motion is going to remain the same. Then we'll go for directional deformation along y-axis. Maximum is 0.216 mm. Strain is 0.00614. Stress is 525.74 megapascal maximum. Minimum, as you can see, is again 8.68 into 10 raised to minus 5 megapascal. Now we'll see the value of safety factor. You can see that this material is little better as compared to stainless steel, as this value of safety factor has increased. So this indicates that brass will be better as a material as compared to stainless steel. Now we will change this material again to CPVC for this boundary condition itself, and let's see what happens. We go to solution A6 and solve once again. We'll first go for total deformation. You can see the maximum value is 6.319 mm, which means the deformation has now increased. You can animate and see the pattern will be the same. Directional deformation is 6.319 mm along the y-axis. The value of strain is 524.89 megapascal. Now the value of stress cannot change. What happens is the safety factor is what is going to change, and this is what you need to check. You can see the value of safety factor is really low. It is 0.09921. This is the maximum safety factor over here. Since the value of safety factor is so low, your body will not be safe under this value of moment and pressure. You have to change, which means that if the application is known, say we are very sure that 2 megapascal is the pressure and the moment is 200 Newton mm, then what you do is you can go for brass as one of the materials and then stainless steel. But do not use plastic in this application. It cannot work because it is going to fail. So you have to be very sure as to what material has to be used where. It should be as per the application. Cost is again a very important factor which people generally argue upon, that plastic is going to be the cheapest, then comes your stainless steel, and finally comes brass. Brass again is going to be costlier. But the life, that is the longevity of brass, is going to be maximum. Then you have stainless steel, and finally reduced one is your plastic. So plastic will not sustain under pressure and temperature accordingly. So you have to decide based on your application overall how you are going to use this valve. So choose the material for static structural analysis based on its pressure and moment value. With this, I end the session. I hope you have understood the analysis. If you have any doubt, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.